In this section, we're going to look a little deeper into solving differential equations using the technique of separation. Let's see, I misspelled that. Pardon me. Separation of variables. And let's recall an example that we've already done to set us up to do some that are a little more sophisticated. I believe we had a differential equation that was y prime equal x times 1 plus y. And as you recall, the way we do that is we'll write y prime as dy over dx, and then separate the variables, so we'll multiply on both sides by 1 over 1 plus y, dy, and at the same time we'll divide or multiply on both sides by dx. And so we end up with this configuration. We've already seen this before. Now, actually, I'm not going to solve this. I want to make a point the way this can be written. And notice that on the left side, the 1 over 1 plus y could be thought of as a function of y. So I'm going to call that function n. And on the right side, the x can be thought of as a function of x. I'm going to call that m. Pardon me for just a moment. Sorry, I had a little catch in my throat. I still have it, but let's see if I can get through this. So m is a function of x, in this case just x. And so we end up with a function of y dy equal to a function of x dx. Now, without loss of generality, I'd like to have both of those on the same side of the equal sign. And so I could have actually subtracted x dx on both sides, and although it's not the same function, I'm going to write on the left side the function of x, m of x dx, plus the function of y, n of y dy, equals 0. And of course, in this particular example, that m of x is nothing more than the opposite of x. Now, one more thing that I want to point out here is that if I would have, I'm just looking at different forms here, if I went back through and divided by dx, I would have something that looked like m of x plus n of y prime equals 0. Now, the point that I'm trying to make here, either one of these forms, we can use separation of variables to solve differential equations that can be put in either one of these forms. So this is a form, or these are forms, for which we can use the technique of separation of variables. To solve. Now, specifically, in this particular form, the variables are already separated. In this form, the variables are not already separated, and because of the y prime. But this form is a technique that is easy for us to apply. So let's look at a particular example, and let me pause to write that example down. Okay, you can see here we're asked to solve the differential equation of the quantity x squared plus 4 times y prime equal xy. Now, it may not be clear by looking at this equation, but we can put it in one of the forms above, that is, we can actually separate the variables. So let's first rewrite y prime as dy over dx, and then multiply through by dx. And so we would immediately get as our first step x squared plus 4 times dy is equal to xy dx. Now you can see, of course, the idea of separation of variables is we want only terms or quantities involving x on one side and y on the other. So on the left side, we have both x's and y's in the fact that we have dy. So we need to divide on both sides by x squared plus 4 so that we get the dy alone. Now on the other side, we have x's and y's also, and so let's eliminate the y's from that side by dividing both sides by y. So our next step would look like 1 over y dy, that's dividing on both sides by y or multiplying by the reciprocal of y on both sides. And then on the right side, we'll have the x divided by x squared plus 4 dx. And you can see now we have separated the variables. So after we've got, in terms of only y's on the left side, we'll integrate both sides. We'll have the integral of 1 over y dy. And as we integrate the right side, we'll have x over x squared plus 4 dx. Now, the integral of 1 over y dy, we're well aware, is the natural log of the absolute value of y. And on the right side, the integral of x over x squared plus 4 dx, what we would do is use a technique of substitution. So let me just kind of remind you of what we would do here. Is we would let u be equal to x squared plus 4. And then du, of course, would be 2x dx. And so you see that our form would end up looking like the integral of x over u dx, but of course we're going to we need a 2x dx to get a du, so to put a 2 in here, we'll have to offset that by a 1/2 on the outside. And then we have a form, of course, that is nothing more than 1/2 times the integral of 1 over u, and the 2x dx is nothing more than du. And so that ends up being, that integral is 1/2 times the natural log of absolute value of u, plus, of course, our constant integration. I'm going to not put that in at this point. And the u, obviously, is x squared plus 4. So I'm putting this over here on the side to make you realize how I'm going to write down this, or why I can write down this next step. So over here on the right side of the problem I'm trying to solve, I end up with a 1/2 natural log of x squared plus 4. And remember, of course, we have that constant integration on the left and on the right, and we're combining them together on the right side. Now, I'm anticipating I may need to change that, and so I'm calling it the constant c sub 1. Now, you might notice that my absolute values disappeared in my natural log. Now, realistically, we have to have the natural log of the absolute value, but x squared plus 4 is always going to be positive. It can't be 0, it can't be negative, it's always going to be positive. So, of course, the absolute value of x squared plus 4 is the same as just x squared plus 4. Okay, so now we're going to take now a little algebra magic, and that's what we have to spend a great deal of time on. When the natural log is equal to something, that means the base of this logarithm, which is e, to the power that is on the right side, that's what the natural log is equal to, is equal to the argument. In other words, the absolute value of y, which is here on the left side, is the base of the logarithm on the left side e to the power that we have on the right side. And that is 1/2 times natural log x squared plus 4 plus the constant c sub 1. Now, the 1/2, recall, in front of that natural log, we could actually use a law of logarithms and write that as a power on the argument, x squared plus 4. But x squared plus 4 to a power 1/2 means nothing more than square root. So we'll write this absolute value of y is equal to e to the power natural log of square root of x squared plus 4 plus the constant c sub 1. And that's part of the exponent. And I hope that you understand where that comes from. Now, the fact that we have e to a power that's a sum, remember the way we can break that apart is we'll say e to the power c sub 1, I'm kind of doing this in a little different order than what we see, times e to the power natural log of the square root of x squared plus 4. Now, pardon me, because of course we know that if we have the same base and we're multiplying, what do? Is we add together the exponent. So I'm just going in the reverse order. Now, e to the power c sub 1, c sub 1 is just an arbitrary constant, so e to an arbitrary constant is just a constant itself. And so we could write this, and we've kind of seen this already, is that, as a reminder, we could call this e to the c sub 1 power as some other arbitrary constant. So I'm calling it c sub 2 times e to the natural log of the square root of x squared plus 4. Now, we've already mentioned previously that e to a power that's a natural log is actually just the argument. So this part just becomes the square root of x squared plus 4. So we actually have the absolute value of y is equal to c sub 2 times the square root of x squared plus 4. Now, we did cover that in the last section, the reason we can write that. And it's important to understand, of course, what does the natural log of the square root of x squared plus 4 mean? Well, it's the power we put on e to get that square root. And so that natural log is, in fact, the power that we're putting on e, and so the result is just the square root. Okay. Well, now we're to a position, and we've discussed this before, that we have absolute value is equal to some quantity. Well, that means the y can either be positive or negative. So we end up with y being either positive or negative c sub 2 times the square root of x squared plus 4. Now, this is a reach in the beginning, but the next idea is that we have an arbitrary constant. Now, we either have a positive arbitrary constant or a negative arbitrary constant, but ultimately that's just an arbitrary constant. So I'm going to replace this, which is just either a positive arbitrary constant or a negative arbitrary constant, with, in fact, just an arbitrary constant that I'm calling c. And so we have y is equal to c times the square root of x squared plus 4 as our solution to this differential equation that we started with. I don't think I'll make a habit of this, but let's practice once again checking that in fact this is a solution to the original differential equation. So on this next page, go to this next page, check y equal c times the square root of x squared plus 4 as the solution to the differential equation that we started with, quantity x squared plus 4 times y prime is equal to xy. Now, to show that that's a differential equation, that means we need to replace the appropriate parts in the differential equation to see that we have a solution. So, clearly on the right-hand side, let's go through this here, x squared plus 4 times y prime is equal to xy. Now, on the on the right-hand side, of course, we have that y from above as a solution is this c times the square root of x squared plus 4. So let's replace it. So we have x squared plus 4 times y prime equal x times c times the square root of x squared plus 4. Now we need to concern ourselves with replacing the y prime. Now, from the fact that we know y is c times the square root of x squared plus 4, to find y prime, we need to take the derivative. Well, of course, we have a constant times the square root, and so that constant will be times the derivative of the square root. Okay? And we're going to write the square root in terms of an exponent to make this a little bit easier for us to do. Okay, well, how do we take the derivative of quantity to a power? We bring the power down, don't we? So we'll have c times our 1/2 times x squared plus 4 to one less, a power 1 less than our original. So 1/2 minus 1 ends up being a negative 1/2. And then we have to multiply with the derivative of the quantity x squared plus 4, which of course is just 2x. Now, as we begin doing a little simplification here, you see that we have a 1/2 times 2, and we have a c times x. And the x squared plus 4 to the negative 1/2 power will be x squared plus 4 to the positive 1/2 in the denominator, but that's nothing more than the square root of x squared plus 4 in the denominator. So now we're going to, we have a way to replace, if you will, the the left-handed side, and let's see what we have. We have our original x squared plus 4, and we're replacing y prime with the fraction cx over the square root of x squared plus 4. And that's supposed to be equal to, and let me rearrange the right-hand side instead of saying x times c, let me say c times x times the square root of x squared plus 4. Now, at first glance, that doesn't look like that those could be, the left and the right side are the same. But remember, on this left side, let me rewrite this fraction. We have cx times, and we'll put that x squared plus 4 in the numerator, and just to emphasize, remember that's a power 1. And into the denominator, rather than writing a square root, I see that maybe I didn't need to do that to begin with. I'm going to write it as x squared plus 4 to the power 1/2 is equal to cx, and that's the question really, isn't it? That's the real question mark. We don't know that this is a solution. We solved and got it as a solution, and now we're checking to make sure our solution is correct. Okay, well, on the left-hand side, we have this x squared plus 4 to the power 1/2 in the numerator and to the power, 1 in the numerator and the power 1/2 in the denominator. So when we simplify the left side, we end up with cx times x squared plus 4 to a power, the top power minus the denominator power. And of course, 1 minus 1/2 is just 1/2, isn't it? And so you can see what's going to happen here. On the left side, we have cx times x squared plus 4 to the power 1/2. And on the right side, we have cx times the square root of x squared plus 4. But of course, this is the same thing as the square root. So we end up with cx times the square root of x squared plus 4 is equal to cx times the square root of x squared plus 4. So what we've shown is that if we use our determined solution and we substitute that into our original equation, it gives us the left side and the right side being equal. So that in fact tells us that we do have a solution. Okay, let's turn the page and look at an additional, or example 2. It's a little different statement, but it's still a matter of using separation of variables to solve a differential equation. In the last example, we've actually found the general solution to the differential equation, meaning that there are an infinite number of solutions. For every constant c that we have in front of that square root, we would have had a solution. So there's an infinite number of solutions. In this example, we're required to find a specific or a particular solution out of the infinitude of solutions. Okay, let's read the problem. Find the equation of the curve that passes through the point 1, 3 with a slope of y over x squared at the point x, y. Well, again, we're looking for the particular equation of the curve. We're not looking for some general idea in the curve that actually goes through a specific point. That's what's going to allow us to come up with the particular solution. Now, the last part of this is kind of an odd way to state that it tells us what the derivative is, doesn't it? The slope at the point x, y is y over x squared. And how do we get slope? We get slope by finding the derivative of y with respect to x. And so the first idea here really is that our y prime in code, we're told, is y over x squared. Now we can easily separate the variables by writing y prime as derivative or dy over dx, and then manipulating a little bit. So we end up with 1 over y dy, and of course we're going to multiply both sides by dx, and so we'll have 1 over x squared dx. And from here we ought to be able to routinely integrate both sides. So we'll integrate on the left side 1 over y dy, and on the right side we'll integrate 1 over x squared, but it's going to be easier if we think of that as x to the power negative 2. And we've been through this many times already. The integral of 1 over y dy is absolute value of y plus some constant integration. Now, the integral of x to the negative 2 power, of course, when we increase the power by 1, we get negative 1. And the reciprocal of negative 1 is negative 1. So we end up with a negative of x to the power negative 1 plus our constant of integration that we're combining from the left and the right to put all on the right side. And again, I'm anticipating that that may change, and so I'm calling it c sub 1. Now, just as we've seen before, of course, x to the negative 1 power is 1 over x, isn't it? So, oops, I apologize. It's the natural log of absolute value of y. And I'm sure you caught that. I'm sorry for my goof. So, the natural log equal to some expression means e to that expression is equal to the argument. So, again, we've been through this. This tells us the absolute value of y is equal to e to the power, okay, negative x to the negative 1 power, which is negative 1 over x, isn't it, plus our c sub 1. And we've seen how this works. For one thing, we can write the right side as e to the power c sub 1 times e to the power negative 1 over x. And then the absolute value of y can be positive or negative. And so we combine all that, as we've already seen in the previous example. We end up with y is equal to some arbitrary constant times e to the power negative 1 over x. Now, we've found the general solution to the statement or to the problem at hand, but to find the particular solution, we need to know the value of this constant that satisfies the condition given. And that is that the curve has to go through the point 1, 3. So using that information, that tells us that if we use an x of 1, then our y value has to be 3. So from above, if our y value is 3 when x is 1, we have the left side being 3, and that's equal to the constant c times e to the power negative 1. Negative 1 over our x value that is 1. Okay, well now, pardon me. So what we're going to do here is we're going to, if you will, we're going to write, I'm tempted to leave steps out, and I apologize for that. We're going to write the right side as c over e to the power 1, since e to the negative 1 is 1 over e. And now I'm going to multiply on both sides by e, and so I end up with c is equal to 3 times e. Okay? So that's the value of c. But we're not finished, because we need this value, okay, to put into the general solution that we had here. So we have y is equal to, now we found out that c itself is 3 times e, and then we have, of course, times e to the power negative 1 over x. But notice that what we have here, and what we have here is e to the power 1 times e to the power negative 1 over x. So this ends up being 3 times e to the power 1 minus 1 over x. That's the two powers basically added together. And 1 minus 1 over x can be simplified. Since 1 is x over x, this becomes e to the power, replace 1 with x over x, so we have the fraction x minus 1 over x as our power on e. And that's the solution, the particular solution. That is, that's the curve that passes through the point 1, 3, and every point on this curve has a slope of y over x squared. The tangent line at every point is y over x squared. Okay, before we, in the next problem, what we're going to see is that we have a problem where separation of variables doesn't work at first attempt. And what I mean by that, of course, is that we can't separate the variables, but there's a technique that allows us to change the problem so that we have one in which we can separate the variables, and then we can go ahead and solve. So let's pause as I get the next problem set up. Well, as you can see, the first statement there, that separation of variables does not always apply. That is, we can certainly have differential equations where we cannot separate the variables, so we must use a different technique. Now, I just mentioned at the end of the last example that what we need to be able to do is to change the differential equation in such a way by introducing a variable, another variable, so that we can transform our differential equation to one in which we can separate the variables. So let's look at this example. I'll show you how we're going to solve it, and then I'll tell you how we can decide whether this is a technique that will work by looking at the differential equation involved. So here we go. Solve the differential equation. Y prime is equal to the fraction 3x plus 2y, all divided by x. Now here's what we're going to do. We're going to introduce a new variable, v. But we're going to do it in this way. We're going to let y be some function v times x. That's the way we're going to approach it. Now, when we do that, that tells us that y prime, to find the derivative of y with respect to x, we're having to find the derivative of a product. That is, we're finding the derivative of v times x. Now remember, v is a function of x itself. So we have to use the product rule to find this derivative. And so the product rule tells us that it's the first function times the derivative of the second, but the derivative of x with respect to x is just 1, plus the second function, in this case that's x, times the derivative of the first function, of course, with respect to x. So y prime is v plus x times dv over dx. So we take our original differential equation and we replace, in this case, the left side, but we're replacing y prime with v plus x times the derivative of v with respect to x. So we end up with v plus x times derivative of v with respect to x on the left side is equal to. Now, on the top, on the right side, of course, we have 3x. And then we have plus 2y. But remember, y is vx. So we have 2 times y, but y being replaced with vx. And all that's divided by x. Now, if we look at the right side, in the numerator, we have x in both terms. And so x becomes a common factor. So we'll take this down a step, rewrite the left side, and on the right side, let's factor out that common factor of x in the numerator. So we'll have 3 plus 2v, the quantity times x, divided by x. And of course, x over x is just 1. So our differential equation reduces, in this case, to v plus x times derivative of v with respect to x is equal to 3 plus 2v. Now, this differential equation is in fact separable. We can separate the variables v and x, and you see that that's all we have now. We don't have any y's at this point. Well, the first thing we're going to do is we're going to subtract v on both sides, and while I'm at it, okay, so that'll leave x times the derivative of v with respect to x on the left, and 2v minus v is v, and so I'm going to rewrite this as, rather than say 3 plus v, as v plus 3. Now, to separate the variables, I'm going to multiply both sides by x, dx, and I'm going to multiply both sides by 1 over x and both sides by 1 over v plus 3. So we end up with 1 over v plus 3 dv is equal to 1 over x dx. Now, we have the variables separated. We integrate both sides. When we integrate the left side, because if we replaced v plus 3 with a u, then du would just be dv. In other words, when we integrate this left side, we get natural log of the absolute value of v plus 3. And on the right side, when we integrate, we get natural log of absolute value of x plus our constant of integration that we've all taken to the left side. I'm going to show you a little different technique than what we've been doing here. Let me remind you, okay? Let me remind you what we would have normally done at this point. Let's see how I can, let's see if I have enough room to do this. One possibility is to approach this as we have been, and that is that we would say the absolute value of v plus 3 is equal to e to the power natural log absolute value of x plus c sub 1. Well, that would be absolute value of v plus 3 is equal to e to the power c sub 1 times e to the power natural log absolute value of x. And that's actually not what I wanted to do. I apologize for my let me well, let's see if I can get myself out of this. So we have absolute value of v plus 3 is equal to, well, e to the power c sub 1 is nothing more than some constant, and e to the power natural log absolute value of x is just absolute value of x. Well, absolute value of x is either going to be plus or minus the value of x itself. So it's either going to be, absolute value of x is either going to be x or it's going to be the opposite of x. And so we have the absolute value of v plus 3 is equal to either a positive or a negative constant just times x. And then we've seen the same idea that since absolute value of v plus 3 is either positive or negative, we're really just going to have plus or minus the right side. And v plus 3 then is going to be some constant times x. Now, that's one way we can get, and we're not finished here. I'm just going to show you another way we can get to that stage. And that other way would be, actually there's 2 or 3 ways we can do this, and I don't know if I'm going to show you a third way, but we could take the, from above, we could subtract natural log absolute value of x on both sides. That is, we can rewrite the above in this fashion. And of course, when we have natural log subtract natural log, that's actually natural log of the quotient of the absolute value of v plus 3 over x. Oops, and that should be equal c sub 1, not plus c sub 1. So that should be equal c sub 1. Now, from here, we would say that the absolute value of v plus 3 over x is equal to e to the power c sub 1. But of course, that's just some constant. Okay, that's just some constant. And actually, some constant. And so then we would have the absolute value as being some constant. Well, the absolute value can be positive or negative, and so it would be plus or minus that constant, which is basically just a constant. And now if you see that we multiply both sides by x, we're at the same stage that we were just a moment ago. We would have v plus 3 is equal to a constant times x. So we don't know whether the constant's positive or negative. So that's a little different approach yet. And there are other things that we can do. And if you have questions about them, then maybe that's something that you can ask me later. But anyway, here we are. We're not finished with this. All we have at this stage is that v plus 3 is equal to c times x. Now, what do we do with that? Well, here's what we do with that. We also know, let me pause and go to the next page. Okay, so here we are. We've got to the point where v plus 3 is equal to c times x. But remember, in the very beginning of this problem, we let y be equal to v times x. So from there, that implies, dividing both sides by x, that implies v itself is y over x. So that allows us to take this value of v and replace it into the result we got a moment ago. So instead of saying v plus 3 is equal to c times x, we'll say y over x, which is v, plus 3 is equal to c times x. Now, we'll clear the fraction by multiplying through with x, so that will leave a y in this first position, plus 3x in this second position, is equal to c times x squared on the right side. And from here we can solve for y, and we would end up with y is equal to c times x squared minus 3x. And there is the solution to our original differential equation. Now, what I'd like to do again in this case is I'd like to check this solution. So let's go about that just for a little bit more practice. Let's check. Okay. Now, remember, what we're trying to check is whether the above is a solution, that is y equals cx squared minus 3x, in fact, a solution to the differential equation, which originally was y prime is equal to 3x plus 2y divided by x. That's what we're checking. So we're going to take this result, and we need to come up with a value for y prime. So when we take y equals cx squared minus 3x and find y prime from that equation, we would get 2 times c times x to the first power. The derivative of cx squared would be 2cx. Minus the derivative of 3x will, of course, just be 3. Now, also remember, we've got y is equal to cx squared minus 3x. That's where that came from. So we take the original differential equation, and we replace y prime with above and y with above. That is, we replace y prime with 2cx minus 3x. And on the right side, we replace y with cx squared minus 3x. Of course, all that right side is divided by x. Let's see where this leads us. Of course, the left side, and I apologize, the left side is 2cx minus 3, not 2cx minus 3x. So we have the left side 2cx minus 3, and we're wanting to know, in fact, that these two are equal. On the right side, as we look at this fraction, notice we have 3x plus 2cx squared minus 6x all over x when we distribute that 2. Well, of course, that becomes, say 3x minus 6x is negative 3x plus 2cx squared all divided by x. Now we see that x is a common factor, and so and of course we're still wanting to know whether these two sides are actually in fact identical. So we see that we can factor out an x from the numerator, and that allows us to reduce the fraction. So we end up with 2cx minus 3 is equal to negative 3 plus 2cx. And in fact, that is true, it's just in a little different order. So we've shown, in fact, that what we found as a solution is, in fact, a solution. Well, that ends this example. But, one, how did I know that that technique would work? And that technique was replace y with v times x. How would I know that that would work? Well, the reason I would know that would work is because the differential equation that we had was called a homogeneous differential equation. And so that's what we're going to investigate next. And we'll pause or stop here and start up with the idea of what this homogeneous stuff is all about. Okay, you can see we're going to talk, as promised, about homogeneous differential equations. But before we do that, we need to understand that we can have functions of one variable, functions of two variables, and then we need to talk about homogeneous equations before we can understand what homogeneous differential equations are. So let me just point out to you that we're used to the notation, functional notation, and we're used to seeing functions like this. F of x is equal to 3x squared plus, let's say 5x minus 7. Nothing fancy. This is a function of one variable. That one variable is x. Now, here we need to introduce a concept of having a function of two variables. And actually, in Calculus 3, we deal with functions of two variables or three variables frequently, but this is something new to us in calculus at this point. So a function of two variables, we would see the notation f of x comma y, meaning what's going to follow will have x's and y's both in them. So we might have something like 3x squared y plus 2y minus x plus 4. So this is a function of two variables. Now, we could also have a function, this will look similar to what we've seen in the previous example. It looks similar, but not the same. We could have a function of two variables that might look something like this. Let's see, 3x plus 2y all divided by x. Now you see that fraction has both x's and y's in it, and so that's a function of two variables as well. Okay. The second thing we need to be concerned about now is what is a homogeneous function. So first, before we can talk about homogeneous equations, a function in, let's say, two variables, f of xy, is homogeneous provided f of, let's say, replace x with t times x and replace y with t times y. So f of tx comma ty is equal to t to the power n times just f of xy, where positive integer. Positive integer. We say the degree of f of xy is 10. In fact, it is the degree. The n is the degree. I shouldn't say we say, but I guess I'm going to. I should really say where. We say n, or we say the degree of f of xy is n. Now, I think it would be a good idea here to look at a couple of examples. In fact, the examples that we have above. So let's look. We'll just say kind of a example one from above about a homogeneous function. Okay. F of xy is equal to 3x squared y plus 2y minus x plus 4. Now, let me point out to you that in this particular example, this is being a polynomial in two variables. To find the degree of the polynomial, we look for the highest degree term. And how you tell the degree of a term is by the sum of the exponents on the variables in the term. So if you look at the first term, 3x squared y, the sum of the exponent of 2 and the sum of the exponent of 1, the degree of that term is 3. The degree of 2y is just 1. The degree of negative x is just 1. And so this has a degree of 3 as a polynomial. Now, let's apply that this function is a homogeneous function. That is, if we replace x with tx and y with ty, then what we'll have is 3 times, instead of x squared, we'll have tx, that squared, and instead of y, we'll have ty. And of course, the plus 2y, y is being replaced with ty. And the minus x, well, x is being replaced with tx. And then plus 4. Now, oh, I have a bad example. Excuse me. I'm using a bad example here. Let me, if you will, this is not homogeneous. Okay, so this is not homogeneous, and if you want to go further, you can figure that out. Now, okay, and the problem is that if you see what we have here, we'll have a 3, and t squared times t, we'll have a 3t cubed x squared y plus a 2ty minus a tx plus a 4. And you notice here that we can't even factor a t out. For it to be homogeneous, we would need to be able to write this as t cubed times f of x comma y. That would mean it would have to be t cubed times 3x squared y plus 2y minus x plus 4. And so you see, that's not true, is it? Okay, that's not true. We don't have a common factor of t cubed, and so this is not a homogeneous function. So let me replace this example, this function, with another. And so here, with example 2, let's say f of xy is x squared y minus 4x cubed plus 3xy squared. Now you see every term here is of degree 3. And that's kind of the giveaway that this will be a homogeneous equation when we're talking about a polynomial function. So we're going to replace x with tx and y with ty. And so we end up with, instead of x squared, t times x, that product squared. Instead of times y, we'll have ty minus 4 times x cubed, but x is tx, that is being replaced with tx. So we have tx cubed plus 3 times x, but x is replaced with tx, times y squared, but y is replaced with ty. And as we see here in this first expression, we have t squared x squared ty, so that's a t cubed x squared y. In the second term, we have 4t cubed x cubed. 4t cubed x cubed. And in our third term, we have a tx times a t squared y squared. So we have 3t cubed x y squared. Now you see that t cubed is a common factor. So we can factor t cubed out. And so we'll have t cubed times x squared y minus 4x cubed plus 3xy squared. And you notice what's in these brackets is nothing more than our original t cubed we have, and in the brackets is nothing more than f of xy, which was our original function. And so this is, in fact, from our definition above, okay, a function is homogeneous if, in fact, f of tx comma ty is t to some power times the original function f of xy. So this is homogeneous. Okay, on the next page we'll do an additional example. Let me pause and write that example down. Okay, in our example 3, we're going to answer the question, is f of xy, which is equal to 3x plus 2y over x, a homogeneous function? So the way we would test that is that we would take the original function and would replace x with tx and y with ty. And so when we do that here, we would have 3 times tx, replacing x with tx, plus 2 times, instead of y, ty, and divided by, instead of x, tx. Now, as we look and see what we've got here, we end up with a common factor of t in the numerator. Okay, let me factor that out to the front. So we have t times 3x plus 2y divided by t times x. Now, normally we would cancel t over t, which is just 1, isn't it? But what I want to do is write that as t to the power 0. And that would be the exponent of 1 subtract the exponent of 1, of course, which is just 1, times the fraction 3x plus 2y over x. And so we end up with t to the 0 times the original function f of xy. And so we can, in fact, write f of tx comma ty as t to some, I said positive integer, I guess in this case it could also be 0. So I misstated a little earlier. But here we would say, yes, it is homogeneous. And in fact, we would say the degree is 0. Now, here's the deal. Okay, let's kind of summarize now, because it seems like I haven't been talking about differential equations. If we have a differential equation which is of the form y prime and the right side is a function of x and y, then we say this differential equation is a homogeneous differential equation. Okay, it is a homogeneous differential equation sorry, I'm getting very sloppy. My notebook is kind of cramped upon the right side, is a homogeneous differential equation provided that the function f of xy, that is the right side of this differential equation, is a homogeneous equation. I mean, it is a homogeneous function, pardon me. Now, so what? Okay, so what? Well, here's the so what. Homogeneous, let me pause, let me write this all out, and then I'll talk about it. Okay, so here's the deal. Homogeneous differential equations might not be separable, but they can be solved by converting them to a separable differential equation, and that's done with using the substitution y equal v times x. So if we know we have a homogeneous differential equation, we can make it separable with this substitution, and when we make it separable, then we can solve it. And it would run much like the example that we did a bit ago before we knew about this idea about homogeneous. So, in fact, more generally, let me write this down. As I was saying, more generally, a differential equation of the form m of xy times dx plus n of x comma y dy equals 0 is a homogeneous differential equation if both of the functions m and n are homogeneous functions. Now, this is, of course, a calculus course. This is not a differential equations course. After you take all of your calculus courses, and particularly if you're either a math major or if you're majoring in, if you're an engineering major, particularly, those two majors will require you to take differential equations. There's a whole course in solving these. And so you'll see many of these types of equations there, and this is a technique you'll use. Let's finish our examples with another homogeneous differential equation. Let me start that on the next page. Okay. Solve the homogeneous differential equation y prime equal x plus y over x. Now you see in this example, and this is probably what you're going to run into in our calculus course, is you're going to have the information that it is a homogeneous differential equation in advance, not that we have to make that decision. It would not be difficult to check that this is homogeneous, but we're given that information from the very beginning. And in fact, as this differential equation stands, it is not separable. So we have to use this technique. Okay, so we're going to let y be replaced with vx. And remember, vx is a function of x. So that implies then that y prime, on using the product rule on v times x, is v plus x times the derivative of v with respect to x. Remember how we did that. It's the first function, which is v, times the derivative of the second function with respect to x. Well, the derivative of x with respect to x is 1. So that's where we get this v times 1. And then it's the second function, x, times the derivative of the first function with respect to x. Well, the first function is v. So we have x times the derivative of v with respect to x. That's where that comes from. Okay. Now, what we do is we replace in our differential equation, let's write it down here, Okay, we have our differential equation, which is y prime is equal to x plus y over x. Okay, on the left side, we replace y prime with what we have above, v plus x times the derivative of v with respect to x. And on the right side, in this fraction, we replace the y with v times x. Of course, that's what we said y was going to be, v times x. And that's all divided by x. Well, then we can see that on the right side, that fraction in this case will simplify because we can factor an x out of the numerator, and that will cancel with the x in the denominator. So that will leave us simply with 1 plus v. Now, what we're going to do next is we're going to gather our v's together. So I'm going to subtract v on both sides. Whoops. And that'll leave x times derivative v with respect to x on the left side, and 1 plus v subtract v, which is just 1. Now, we can easily separate here. Okay, so I'll divide both sides by x and multiply both sides by dx. And so that will simply leave dv is equal to 1 over x dx. Now we integrate on both sides, and when we integrate dv, we just get v. And when we integrate 1 over x dx, we get natural log absolute value of x plus a constant. Now, recall that v from up above is, remember the y is vx, and so when we solve that for v, we get v is y divided by x. And so in place of v, we put y divided by x, and that's equal to the natural log of absolute value of x plus c. Now, what we can do here, of course, what we could do here, pardon me, what we're doing is looking for y, aren't we? So we could easily solve for y here by multiplying on both sides by x. And so we'd have x times natural log absolute value of x plus c times x. So this would be one form of the solution. Now, I want to show you an alternative here, because this might be something that we would see as an answer, and we don't need to understand where in the world it came from. So rather than solving for y directly, as I've already done, what I'm going to do is first solve for natural log absolute value of x. That is, I'm going to subtract c on both sides. Now, the fact that I'm subtracting c on both sides, rather than say subtract c, remember c is just a constant, arbitrary, and we don't know whether it's positive or negative, so we'll just say plus c, okay? We'll just say plus c is equal to the natural log absolute value of x. Remember, we don't know whether c is positive or negative, so whether we have a plus or a minus in front of it doesn't really matter. It just cleans it up a little bit, makes it look a little better. And anytime we have the natural log of something is equal to, that means e to the other side. In other words, from what we have here, we can gain that the argument absolute value of x is equal to e to the power y over x plus c. And then we've seen this before, that that's nothing more than c times e to the power y over x. Because after all, e to the power c is just another constant, okay? And so rather than just changing subscripts, I'm just calling that c, and that's where that came from. So that tells us, since the absolute value of x is something, x is either plus or minus that. But once again, we don't really care whether c is positive or whether c is negative. is any arbitrary constant. And so the plus or minus gets eaten up by this constant, basically. And so x is equal to c times c times e to the power y over x. So this is another way that the solution can be written. Now, this, of course, is not solved. This is not solved for y, so we don't have y is equal to. This is just another form of the solution, where it's, in fact, not even solved for x directly. So you might see that as a solution. Okay, what we're going to do in the following pages on this section is we're going to talk about something called orthogonal trajectories. And to explain that, I need to give an example. So I'm going to pause here, and we'll start this up after I get things set up for it.